All right, so in the previous video, we were talking about different types of regions, case 1 and case 2. And now here we are going to do the actual, the whole integration. So now I gave you a function here, 4x y minus y cubed. So this is some f of x comma y. And what we're doing is we're going to project these curves onto these graphs. Now, luckily for us, because we already since we're looking for the bounded region of square root of x and x cubed, we already did that in the previous example. We even set up both cases. So all we really got to do is just find this volume. So now before I start doing the integration, I do want to show you what exactly is happening geometrically. So geometrically, this is what's happening. So you got your x, you got your y, you got your z, and you got this function in here of x and y. So I don't know what the function looks like, but let's just pretend it looks kind of like this. That was my function. That one is this guy. And what we're looking at is we're finding the volume of these two guys. Okay, so you got these two guys, and they look something like this. And what we're doing is we're projecting this guy onto here. So what we're looking at is finding the volume of all of this guy. So what exactly is that volume? All right, just to give you a geometric representation. Okay, now it really doesn't matter which one you want to use. That's not relevant. But if you want, you can use region 2 or region 1. Doesn't really matter. I'm going to use region 1. Okay, so I'm going to take the integral, the double integral, and then I'm going to have 4xy minus y cubed. All right, so I'm going to let my y's be from x cubed all the way to square root of x. Now, because these are x's, that means that my inner integral should have a dy. So it's always kind of the opposite, because that's what y equals. And then my outer integral is going to be dx, and I'm going to have the 0 to 1. Now, remember, you always want your outer integral to have numbers, because if they don't, you're going to end up with a whole bunch of variables, and you really mess that up. Okay, so the inner integral should always have your functions. All right, so now let's go ahead and evaluate this guy. So we're going to start off with our inner integral. So remember, this is with y, so we're going to take the antiderivative with respect to y. So the inside integral is just going to be 4x, then y squared over 2, minus y to the 4th over 4. This is going to be from x cubed all the way to square root of x. So you can see that this guy is just going to be the integral from 0 to 1. So simplifying this, you get 2xy squared minus, I'm going to write it as 1/4 y to the 4th. From x cubed all the way to square root of x dy. Ooh. Mistake. Should be an x. All right, so now let's plug in all those. Let's plug in that into the y. So you got integral from 0 to 1 of 2x. And then I'm going to put parentheses squared minus 1/4 parentheses to the 4th. So that will be my first part. And then I'm going to use fundamental theorem of calculus again. 2x parentheses squared minus 1/4 parentheses to the 4th dx. And what I'm going to put in there is going to be these limits. So I'm going to first put in the square root of x. And then I'm going to put in the x cubed. All right, so this is going to give me the integral from 0 to 1. So this guy just goes away, and I'm just going to be left with 2x squared minus, so this one you're going to have an x squared left, because this is in a power to the 1/2. 1/2 times 4 gives me 2, so it's going to be 1/4 x squared minus, So I'm going to distribute this negative to both of these guys. So this is going to be, this is x to the 6th, so x to the 7th, 2x to the 7th. Then here you can see that we got a negative and another negative. That's going to give me a positive. So then you're going to get a 1/4 x to the 12th dx. I had to do this really careful or else I'm really going to mess this up. Okay, that looks pretty good. I'm going to combine these two guys up. This can be 8 over 4, so which is going to give me 7 over 4. So I'm going to get integral from 0 to 1, 7 over 4, x squared minus 2x to the 7th plus 1/4 x to the 12th dx. All right. So now let's just take the antiderivative of all of this, because now we just have only x's. Okay, we did kind of the rough part already. So this is going to be 7 over 12 x cubed minus 1/4 x over 8 over 4. And then plus, I'm going to have the 13 on the bottom. That's going to be 1 over 52 x to the 13 from 0 to 1. Alright, so I'm going to have 7 over 12 times 1 cubed minus 1 to the 8th over 4 plus 1 over 52 times 1 to the 13th power. Everything is just goes to 0. And what you should end up getting is 55 over 156. Alright. So there's a lot of algebra in here. There's a lot of stuff going on. So they're not the most prettiest integrals, especially because you're dealing with functions. Things are not really going away. They're actually adding on to this particular integrand. So you need to make sure that you keep everything with care. You don't want to do the things very, very fast. You want to make sure that you do things pretty slow, but also move fast enough in the sense to not be able to lose time in an exam. Okay, so that's how you would do that problem. So let's go ahead and do a couple more. All right, so let's say we want to do the double integral over the region R. And another mistake here, let's just say this is R. Where R here is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. All right, so the first thing that you always want to do is set up the region. Okay, so let's go ahead and take a look at what this looks like. So the first one is y equals 2x squared. So that's like a very skinny parabola that kind of looks like this. The parabola looks like this. So let's say this is y equals 2x squared. And then we got the y equals 1 plus x squared. So 1 plus x squared is a parabola, but shifted up 1 unit. So it looks kind of like this. All right, so the region that I'm looking at is this region right here. So this blue one is y equals 1 plus x squared. All right, so when you can imagine that this thing is being projected, this region, you're lifting it up, imagine that it's coming right at you, and you want to find that particular volume embedded into this x plus 2y, which is, I think, is a plane. All right, so this is kind of obvious that you probably would be better off using case 1. Case 2 seems pretty convoluted. Case 2 seems like it's 2 integrals in 1. So, and I'll tell you what the case 2 would actually look like. But right now, it looks like case 1 will be the easiest one, right? Because you can see that it goes through the bottom graph, which is the 2x squared, and it goes through the top graph, okay, which is going to be the 1 plus x squared. So when we set up the integral, let's go ahead and set it up. So we know that it's going through the first graph, which is y equals 2x squared. So that's where the first graph that it's going through. And it's coming out the blue graph, which in that case is going to be the 1 plus x squared. All right. So now let's write down our function x plus 2y. The first one should be, because this is functions of x, so the other one should be dy. And now all we really got to figure out is what are going to be the limits of integration of the x values. So in other words, this is going to be, so since we're going up and down, that's going to be the y, so we're looking for the x values that are where these two guys intersect. Well, that's going to be really easy. All we really got to do is just set them equal to each other. So 2x squared equals 1 plus x squared. All right, so now let's go ahead and move the x squared over. So you get x squared equals 1. Take the square root and add plus or minus. So x equals plus or minus 1. So this guy is going to go from -1 to 1. All right, so now let's go ahead and take this double integral. So we're going to first start off with the integral, which is in terms of y. So we got the integral from -1 to 1. And then this guy's going to be x squared. No. With respect to y. So it's xy plus 2y squared over 2, which gives me y squared. It's going to be from 2x squared, 1 plus x squared dx. So this is from -1 to 1. I'm going to plug in that into the y, okay, because that was what we just integrated. So x 1 plus x squared plus 1 plus x squared minus, and now we're going to have x 2x squared plus 2x squared. Okay, so this is going to be equal to the integral from -1 to 1. So you're going to get x plus x cubed. And then when I FOIL this guy out, what is that going to give me? So this is going to give me 1 plus 2x squared plus x to the 4th. That's this guy. Minus, so this guy right here is going to be 2x cubed. This guy over here is going to be 4x to the 4th. So it's going to be a minus 4x to the 4th, because notice that there's a minus and a minus there, a minus and a plus there. And then you have a dx. Alright, so what is this going to give me when I make everything all, try to make it nice? So I have, let's see. So this guy and this guy gives me -3x to the 4th. Then this guy and this guy give me -x cubed. You have a lonely 2x squared. You have a plus x and a plus 1. Okay. All right. And now all we got to do is just take the antiderivative. So this will be -3x to the 5th over 5 minus x to the 4th over 4 plus 2x to the 3rd over 3 plus x squared over 2 plus x from -1 to 1. Now, one of the things that you can do is you can use symmetry if you know how to work with that. If something is symmetrical, you can kind of change this order of integration from 0 to 1. So things that are symmetrical about the origin, if they're an odd or even function, you can use that type of terminology. So remember that what that really means is that if you have like an even function like this, and you were going from -1 to 1, if you have a power of a power function that has an even power, you know that that's just going to be double. So you can just do the same thing 0 to 1 of whatever that function may be. So you can do that. And if you have something that's an odd function, so kind of like a x cubed, kind of looks like that, and you're going from -1 to 1, we know that that area is just going to go to 0. So the integral from -1 to 1 of that function is just going to go to 0. So if you can also use that to kind of help you, because you know that those things are going to go away. So for example, if you were to do that, this guy, you would have, this one would go away, and this one would go away. So you just have to take the integral of the other guy, of each of them, and then just double them. So you'll see with this guy, once you do all of that stuff, you're going to get 32/15. Okay, so again, these are not the most fun problems, but you can definitely do it. Now, before we continue, I do want to make a little note that you could have used type 2 if you want to, but it's a lot more difficult. So if you wanted to use type 2, this is what you would have done. So you would see that this intersects this outer part and this inner part. So you would do the integral from this part and then this part. And notice that it goes through the second part and then out this guy. So you would have had 2 double integrals. This would have been a lot harder to work with as opposed to just this one. So you always want to be very careful with which one you would want to do over the other. So now let's finally do this last problem. So let's go ahead and set up the integral. So this is really important. There's going to be some problems where you just have to set it up. So let's set up the integral. Okay, so that means we don't have to evaluate it, but we do need to put in a whole bunch of other stuff in it. And we want to know what that integral would be when you have y equals x minus 1 and the parabola y squared equals 2x plus 1. So let's just go ahead and quickly graph it. So y equals x minus 1, so that's going to be like y-intercept -1, go up 1 over 1. And you can see that this is going to be the equation of a line. This guy, y squared equals 2x plus 1. This is just a parabola. Okay, so it's a parabola shifted over. So we can actually write that as a regular conic, but it's a horizontal parabola. We can factor out a 2. And you can see that this parabola is shifted to the right, to the left, 3 units. Just shifted to the right 3 units. So 1, 2, 3. It's going this way. And it's a happy parabola, so it's going to go something like this. It's going to look something like this. Whatever this may be. I don't know if it crosses through there, but we'll go ahead and see. Okay. So we have something that kind of looks like that. Alright, so now let's go ahead and find what would be probably the best case scenario. So again, in this case, it seems that if I go up and down, it'll be really hard, because if you see, if I go up and down, I have 2 regions here. So let me divide these 2 regions. I have the one you have the 2 parabolas up and down, and then you have the other region, the line, and another parabola. So that's another double integral. So I'm going to save myself from that. I'm going to use type 2 in case 2 instead. So going from the parabola over to the line. So you can see that at every line, a little arrow that I put is always going to go through the parabola and then out from the line. Okay, so that would be better if I just use case 2. But in order for me to use case 2, it would be useful if I have everything in terms of x. So let's go ahead and set up my double integral. So I'm going to have my double integral here. The inside is just x and y. Because we're doing case 2, we're going over in the x direction. Okay. So what would this be? So we're going to look at all the values of x in this case, dx, because we're going in the x direction. All right, so what would be my lowest function? So my lowest function, or my lowest equation, would be the parabola, because that's where it's entering. So the parabola in this case has an equation of y squared equals 2x plus 6. So all we really have to do is make this in terms of x. So I have to solve for this, minus 6. So 2x equals y squared minus 6 divided by 2. So you get that x is equal to 1/2 y squared minus 3. So that's what's going to go in here. X equals 1/2 y squared minus 3. All right. So now let's go ahead and do the top guy. So notice we need to get this in terms of x as well. So that's just this line, which was, if I just add the 1 over, you'll see what we get. So you'll just get x equals y plus 1. So the top guy is going to be a y plus 1. Right? And now finally, so now we got our x's, now we just got to get our y's. Now, unfortunately, we don't know where they intersect, so that's pretty easy though. Let's just go ahead and set it equal to each other. So notice we have this guy right here and this guy right here. Let's go ahead and figure out what our y value should be. Remember, we're looking for y. So I'm going to set them equal to each other. So y plus 1 is equal to 1/2 y squared minus 3. So what I'm going to do is I'm going to minus the 1 and minus the y. So you're going to get 0 is equal to 1/2 y squared minus y minus 4. And now what I'm going to do is multiply everything by 2. So you get 0 equals y squared minus 2y minus 8. So that seems a lot easier to work with as opposed to, you know, with the 1/2. So I can factor this guy out. y, 4, 2. This should be negative and positive, so you can see that y equals 4 and y equals negative 2 would be my value. So this is what's in it. This should have been a little lower. Okay, so then in that case, your lowest y value should be negative 2, and my highest y value should be 4. Okay? All right, and this is the setup. We just want to set it up. We don't want to evaluate it. This would be my solution for this problem.